Okay, let's get started. We're gonna dial it back here and just go through the requested questions. So we're gonna start at the top here and kind of work our way down. Here we go. The first requested problem to kind of go over is a rate conversion. So rate conversions are, in concept, not that different from any other kind of fraction-based conversion, where you have the metric to metric ones, which are, just the King Henry died, blah, blah, blah. All the other ones are fraction-based, or I guess conversion factor would be the more correct term. The thing that's different, I guess, about rate conversions is that you have to convert 2 units at the same time, or at the very least in one line. So I'm going to choose to do number 2 here, and that is 105 miles an hour to meters per second. So is it 105? Yep. Miles per hour, and we're going to go to meters, or maybe I should write this just out, meters per second. Now, the way that I would recommend doing this is to write it like this. So 105 miles, I would recommend doing that. And my reasoning is going to be that this helps visualize the conversion factors that you need to set up. So the first thing we're going to do is we're going to set up conversion factors for miles to meters. So this is kind of our usual setup. We have to do a 2-step kind of thing here. So we have to go, you can do a couple of things. I'm going to go miles to, I'm going to go miles to kilometers, and then kilometers to meters. So there's 1.61 kilometers in 1 mile and 1,000 meters in 1 kilometer. And the reason that we set this up this way is so that we can do miles and miles, kilometers and kilometers, and that leaves us with meters as our final unit kind of on the top there. Then we need to do our time unit. So this I'm going to also do in 2 lines. And putting it on the bottom here is pretty important because you need to end up with your time unit on the bottom of the fraction. So since we're starting with hours on the bottom here, we're going to put it on the top. And we're going to go from hours to minutes, and then minutes to seconds. And so by setting it up this way, we can cancel hours with hours, minutes and minutes, and that leaves us with seconds on the bottom, which is what we want. Because now, if we do 1 hour is 60 minutes, and in 1 minute is 60 seconds, whatever number we end up with is going to have the units of meters on the top and seconds on the bottom. So once we have, by setting these units up, as long as we put the right numbers in our conversion factors, we're fine. So I'm going to rewrite the math just so it's a little bit cleaner, kind of without all the units there. And doing all of that out, we would get 46.94. And then that would have the units, which is what we wanted, of meters per second, or maybe we should stay consistent here and do meters per second. So that's a rate conversion. Basically, the challenge for any of these conversion factor ones is figuring out what the pathway is to get from one to the next. Yeah. Moving on. So we'll keep going. And the next one we wanted to do was friction. Okay. So with friction, the formula that we need is force of friction is mu times the normal force. Where mu is the coefficient of friction, it is a number value that basically represents the amount of friction between 2 surfaces. So we'll start with, let's just do number 2 first. So wood block is placed on a wooden table. How much force is required to start the block moving? So There are two different coefficients of friction for every surface, the static coefficient and the kinetic coefficient. The static coefficient is what will enable you to calculate the amount of friction you are required to overcome in order to start this object moving. So we would need to find our coefficient of friction. It's wood on wood, so that is up here. It's 0.44. So the force of friction is going to be 0.44 times the normal force. And now we get to the problem of, well, what the heck is the normal force? If we were to draw a free body diagram of our object here, we know that we would start with the force of gravity. There's a normal force holding the box up. There is the force, whoa, what did I just do? No, nothing. Okay. There is the, oh, I know what happened. That moved. There's the force of friction opposing us, and then we'll just call this force applied. Technically it's a normal force, but moving on. The thing to realize is that in this case, because the box is not accelerating up or down, the normal force must be equal to the force of gravity. Because the acceleration in the vertical is 0, the net force must also be 0. So that means the surface must be exerting exactly the same amount of force as the weight of the object pulling it down. So that means that we can replace, we can say force of friction is 0.44 times the force of gravity. So instead of normal force, we're going to swap in force of gravity. And Fg is calculated as mg, where g is always 9.8 meters per second squared. So our force of friction is going to be mu, which, we know what that is. 0.44, and the mass of the object is 1.5 kilograms times 9.8, which would give us a force of static friction of 6.468 newtons. Okay, so that's the amount of friction that it would take to get the object moving in the first place. Question 3 is, what do we have to do to keep it moving at a constant speed? So for a constant speed, that's going to also kind of tell us that horizontally, if we're moving at a constant speed, that means our net force horizontally must also be 0. Because at a constant speed means no acceleration. No acceleration means no net force. That means the force that we must apply must be equal to the force of friction. So if we find the force of friction, then we're going to get, how much force we have to apply. The catch here is that now that we're moving, we now need to apply kinetic friction. So kinetic friction is typically lower than static friction. And so that's going to mean that it is easier to keep something sliding than it is to start it sliding. But what's nice is really this calculation doesn't change much. The force of friction is still going to be the coefficient, but the coefficient of kinetic, please scroll, is now 0.24. The mass is 1.5, and gravity is still 9.8. We're still calculating, right? This is Fg. And if we do that, then that gives us whatever value that happened to be, which was 3.528. So that value is the amount of force necessary to keep the object moving at a constant speed. If we want to speed it up, if we want it to accelerate, we're going to need to apply more force than this value. This value is what is required to keep it moving at a constant speed. So what do we do? Well, let's pretend that we're playing around in perfect physics land where there is no friction. Let's think about what would happen if there was no friction in this scenario. So number 4, what would happen if we wanted to accelerate the block at 4 meters per second squared in a scenario in which there was no friction? This would become very, very simple. We would just be using Newton's second law. So Newton's second law, if we have a 4 meters per second squared acceleration, the mass is 1.5. So if we multiply by 1.5, that tells us that the force necessary in the absence of friction to accelerate it at 4 meters per second squared is going to be 6 newtons. So now, how do we put these two things together? Well, because we're not playing in perfect physics land and there is friction, let's see if we can kind of make the logic statements here. If this value tells us how much force is required to meet friction, like to compensate for the fact that there is friction, and this value tells us how much force is required to accelerate our object, then our applied force just needs to be the sum of these two. So if we do our, well, let me write them in the correct order here. So if we first apply our 3.528 newtons to meet friction, and then add 6 newtons on top of that to accelerate it, then we get a total amount of force of 9.528 newtons. And that amount of force is basically doing two jobs. It is meeting the friction and providing enough force to accelerate at the rate that we've determined, so 4 meters per second squared. So that's conceptually what we're doing. We have to meet friction and then give enough extra to accomplish our acceleration. All right, moving forward. Next is the vectors. Yeah, okay. So for the vectors, what we're going to need to do is we're going to need to, let's just pick question 3, I think, because that's going to kind of involve all of the skills from 1 and 2. So question 3, find the resultant, which basically just means the sum, like adding all these vectors together, including the magnitude and the angle. There are 3 vectors. They are A, B, and C. We need to break them up into components before we can add them together, because these vectors are not on the same, they're not collinear, meaning along the same line. Therefore, on their own, they are not able to be just added together. You can't just do 50 plus 40 plus 65. No. What you can do, though, is you can figure out how much of each vector is pointing along each axis, and then that will enable you to, you can add those together, the components together, and then kind of put them back together. So just to start here, this would be FAX, so that is the x component of vector A, and this would be FAY, the y component of vector A. Then we would have this being, FCX, and then this would be FCY. The way that I drew it, you would technically have this being FBX, and then we can do this. This is FBY. You could theoretically make other triangles. We're just going to go with this because that's where I put the angles. Let's just go with that. So we need to figure out what each of these x and y components are. Do them one at a time, and we'll start with A. So I'm going to redraw the triangle here. The hypotenuse is 50. This is FAX, and this is FAY. Here's the right angle, and the angle in here is 20 degrees. So we need to use our SOHCAHTOA, and that'll help us choose the right trig function. We'll start with FAX. That is the adjacent side of this triangle. So we're going to use cosine. So cosine of theta is adjacent over the hypotenuse, and that means cosine of 20 degrees is the adjacent, which is FAX, over the hypotenuse, which is 50. I would recommend doing 50, so multiply by 50 on both sides. You get 50 cosine 20 equals FAX. And then if we calculator that out, that gets us to 50 cosine of 20 is 46.98. Son of a gun. Dude. Okay, moving on. 0.98. Then for the y component, we're going to use sine. Sine theta is opposite over hypotenuse. So we have sine of 20 equals, the opposite is FAY over 50. And so if you multiply by 50, we get 50 sine of 20 equals FAY. So FAY is, just confirming all my numbers, yep, 17.10. Okay, so we do that. And now, to kind of move forward, we have to, what did I do? No, everything else seems fine. Okay. So now we do the other ones. We'll do B. So B is going to be 40 newtons at 55 degrees. So we'll do that, and we'll go here. This is 55 degrees. This is 40. This is FBX, and this is FBY. So if we do cosine, oh no, this is tricky, right? So cosine of 55, in this case, so remember, SOHCAHTOA, cosine is adjacent over hypotenuse. In this case, the way this triangle is set up, the adjacent is the y component. So this is actually FBY over 40. So if we multiply by 40, 40 cosine of 55 equals FBY, and FBY is 40 cosine of 55, 22.94. Let's just see if my previous work agrees with that. It does. And then that would give us, I'm just going to kind of jump a little bit so that I have time to write this all out. FBX is going to be, this is important. So FBX is going to be 40 sine of 55, which is 32.7, call it 7. Is that what I wrote? Let me make sure. Yeah. Now, being very careful here, noticing that FBX is actually pointing in the negative direction. So when we add these together, that is going to be extremely important to do. Last is C. So C, we would have like this. This is 45 degrees. This is 65, FCX and FCY. And then we do, so this is a 45, 45, 90 triangle. So that actually does mean that, so cosine would be FCX over 65. So 65 cosine 45 equals 45.96. And that is going to be negative, so FCX is negative 45.9, whoops. Come on, 0.96, and FCY is also negative 45.96 because we're pointing to the left and down for our two components. And so with all those components, with the correct signs on all of them, we then look over here. So if we're looking over here, we're just adding all of the components together. And we can do that. We can add those components because they are collinear. All the x components are on the x-axis, and all the y components are pointing along the y-axis. So those are addable. Now we have our sum. We get our fx and our fy of our new thing. To figure out what the end result of this is going to be, we have an fx of, so I'll do this here. This is 31.75, and we have a y of 6.22, and those are both technically negative. This could be our sort of new vector, and we'll just call that f. So the magnitude of f is actually pretty easy to do. it's just going to be Pythagorean theorem, a squared plus b squared equals c squared. And so if you do 31.75 squared plus 6.22 squared equals c squared, do the math of it all, and you get that f is 32.35. For the angle, that's the trickier potentially part. For the angle, I'm going to redraw this over here, which I should have done in the first place. My bad. This is, scroll please, 31.75 and 6.22. So 31.75 and 6.22. Depending on where you want to draw your angle, this is slightly different, but we need an inverse trig function to make this work. I'm going to choose tangent. So tan theta is opposite over adjacent. So we have the two sides. The opposite side is going to be this guy, so 6.22 over 31.75. And so you have to solve that fraction, so like actually put it into your calculator, and you get tan theta is 6.22 divided by 31.75, and that is 0.196. Now, to finish this, we have to use the inverse trig function. So that means inverse tangent, which is just a different, well, it's the, you like hit shift tangent on your calculator. Inverse tangent gets rid of tangent, and you have to apply it to both sides. So if you do inverse tangent of tangent, that just gives you theta, and then you do inverse tangent of that number, and it gives you 11.08 degrees. So that would be 11.08 degrees in there. And then if you did the other angle, it would just be 78.92. So there's that. That's your vector solution. Do I agree with myself? I sure do. Math is math. I win. Okay. Moving forward. Kinematic equations. Let's do C. How long will it take a cheetah to reach 27 meters per second from rest if it can accelerate at 4.6 meters per second squared? The kinematic problems typically all start the same way. So assuming that we have a non-zero acceleration, these are the 5 possible things that you could have. You're not always going to have all of them. You're not always going to need all of them. What you have and or need will depend on the problem. So let's just keep going here. How long will it take means delta t is our question mark. We're reaching 27 meters per second. That's our VF. From rest, that's our VI. At an acceleration of 4.6 meters per second squared. We don't have delta x. We don't need delta x. It's not part of the problem, so we just don't care about it, and that's fine. The equation we would need is VF equals VI plus A delta t. And we know that we can use it because we have VI, we have VF, we have A, and delta t is the thing that we want, so we should be good to go. 27 equals 0 plus 4.6 times delta t. This basically drops, so you get 27 equals 4.6 delta t, divide by 4.6. And making sure that I'm not a moron, we get a delta t of 5.87 seconds, which is the answer. Sure, I rounded up a little bit too much, but I think we can forgive me. This one is the gross one. I'll do C. So it's the same sort of start, right? So it's delta x, VI, VF, A, and delta t. What do we got? We have... starts from rest, that's 0 meters per second for our initial velocity, accelerates at 8 meters per second squared. How long will it take the car to travel a displacement of 250 meters? Delta t is our question mark. We don't have VF, we don't need VF, so we don't care. The equation delta x equals VI delta t plus 1/2 A delta t squared. How do we know that this is the one we can use? We should do our usual checking of things. Delta x we have, vi we have, a we have, and we might say, oh no, I see delta t twice. That ends up not being a problem, and I'll show you why. So delta x is 250, vi is 0. So if we write this out, this term, 0 times delta t, is 0. So we get 250 equals 1/2 of 8 times delta t squared. And then it's 250, 1/2 of 8 is 4 times delta t squared, divide by 4. And we get that, what the hell is it? So 62.5 equals delta t squared. Take the square root, and we get a delta t of, 7.9 seconds. Which, do I agree with myself? I do. All is well. Yeah, so the question of like which equation is the one to use really does boil down to this process of what information am I given, what information am I looking for, and then by kind of process of elimination, right? This problem up here did not require delta x, like it wasn't even in the problem, and this one didn't have or need VF. So because this equation doesn't have delta x, it's the one to use. Because this equation doesn't have VF, that's the one to use for that one. So if you can just kind of parse through this whole what do I have, what do I need thing, you'll be a-okay. Okay, motion graphs. We're going to jump straight to the velocity versus time graph. As a general note, for the position versus time graph, the slope ends up being the velocity, because slope is rise over run. And in this case, the rise is the change in position, which is delta x, and the run is change in time. Delta x over delta t is the definition of velocity. Kind of a similar thing applies here. In this case, the slope is the acceleration, and it's the same logic, the rise over the run. The rise is the change in velocity, delta v, and the run is the change in time, delta t. Delta v over delta t is the definition of acceleration. And then as far as the area goes, the area under the graph of a velocity versus time graph is the displacement. The reason that that works is because the area in general is some version of base times height, where the base in this case is the time, and the height in this case is velocity. So if we look at the definition of velocity, it's displacement over time. So if we, for example, multiply by delta t, we get that the displacement is the velocity multiplied by the time. So if we do the base times the height, where the base is time, the base is time, and the height is velocity, then by definition, the area is the displacement. And so how you actually accomplish that, if you want to know the overall displacement of this particular graph, you find the area of each shape. And positive and negative does matter here. So for this one, we'd be looking at, let me choose a color here. Can you stop doing things? Okay. So this would end up being, we'd have to look at the base and the height. So this is a base of 4 and a height of 15. So rectangle is base times height. 15 times 4 is 60. This is a triangle, base of 2 and a height of 15. So the area of a triangle is 1/2 base times height. So 1/2 times 2 times 15 is 15. And then you kind of just do the same thing. So we have 60 and 15 above the line here. And then this triangle gives you 15 as well. So 60 plus 15 gives you 90. Then down here, if you find this little tiny triangle, that's -5. And this is a base of 4, and a height of -10. So that's a -40. So -5 and -40 is -45. 90 plus -45, or like 90 minus 45, gives you 45. And why, like, what is happening here? Essentially, if we think about what this graph means, this is the velocity. So this whole, so like this area, it's like this part, and then this part, it's moving at a constant, it's moving at a positive, not a constant, it's moving at a positive velocity, meaning forwards. And then this sort of bottom part here is moving at a negative velocity, meaning backwards. So all of the like area above 0, that's where you're walking forwards. And all the area below 0, that's where you're walking backwards. So like this object went forwards, 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 slowed down, stopped for a little while, moved forwards again, then started moving backwards. And so he kind of walked forwards a bunch and then walked backwards. So his total displacement from where he started is 45 meters. But like in that trajectory, he walked forwards 90 meters. That's what that means up here. He walked forwards 90 meters, then walked backwards 45 meters. So he only ended up 45 meters from the original starting position. That's what that means. Moving forward to projectile motion. Okay, so a cannon fires a cannonball 34 meters per second from the top of a building. If the cannonball lands 235 meters away, how tall is the building? So here we go. This is where we're going to kind of divvy some things up into x and y. In the x, we're going to have a velocity, we're going to have a displacement, and we're going to have a time. In the y, we're going to have a delta y. We're going to have a v initial, a v final, an a, and a t. Kind of our standard stuff. We don't have an a in the horizontal because it's not accelerating in the horizontal. And we only have one v because it isn't accelerating. It isn't changing its velocity. And that's kind of a key here. So if we land 235 meters away, that's 235 meters of horizontal displacement. It fires the cannonball at 34 meters per second. And that's kind of everything we know, right? We have to infer some other stuff. First, the acceleration of gravity, in this case, we're going to write it as negative 9.8 meters per second squared, which we need to do because this is like an actual, x and y. We do have to consider down as negative here. Go away. Then the other thing we need to infer is that if we're launching it horizontally, VI is 0. So we're not launching it up or down. We're just kind of shooting it sideways. So that means by definition, its initial vertical velocity is 0. Its horizontal velocity is 34 meters per second, but its vertical velocity initially is 0. We can see that we have a bunch of things that we don't know. So now the question is, how do we get to the final thing? First of all, what is the final thing? It's how tall is the building. So delta y is what we want to know. VF in this case doesn't end up mattering. So we can kind of forget about VF. It's not needed for the problem. It's not asked about. It's not given. So that means if we want to find delta y, we need to know the time. So how do we find the time? The key here is that it connects over to the horizontal. The only thing that is shared between the two is the time. So if we can find the time over on the horizontal side, that is the time for the vertical side, and then we're good to go. So V is delta x over delta t. The V is 34. The delta x is 235 over delta t. So if I multiply by delta t, I get 34 delta t equals 235. Now I divide by 34, and I get 235 divided by 34. Gives me a time of 6.9 seconds. So that means I can rewrite this here, 6.9 seconds, and I can write it over here, 6.9 seconds. Now that I have that, I am basically set up to finish this, where we're going to use a version of our displacement equation. We're just swapping delta x for delta y. And then filling in, VI is 0, delta t is 6.9 seconds, 1/2 of negative 9.8 times 6.9, and then that's going to be squared. So we can drop this term to 0, so that's 0, plus, I'll do this slowly. We do have to square only the time. And that is going to end up being 47.77. Then if I do delta y and I do that times 9.8 times 0.5, I get negative 234 meters. Do I agree with myself? Yes, I do. Now, why is this negative and the answer is positive? Well, it has to do with what this means. Delta y is your vertical displacement, meaning from where you started to where you ended. So if this is our building, this is where we're starting, and this is where we're ending. So if this is our drop, that is our vertical displacement, which is negative. So we're going from up high down to 0, which is the ground. Therefore, the height of this would just be the absolute value of that, which is just a height of 234 meters. Meaning, because we are launching this thing from 234 meters high, it will go down 234 meters, or a negative vertical displacement, in order to hit the ground. Hopefully that clears that up. Cool. We're cruising. Then we get to the momentum stuff. Inelastic and elastic collisions, I believe, were the last things we wanted to know about, which is great. We're making good time. Okay. So, collisions. Something that can help here are diagrams. So I'm going to draw a diagram for our first problem here. A stationary 90 kilogram student catches a large 15 kilogram medicine ball. If the ball was moving at 6 meters per second, how fast will the student and the ball together be moving after catching the ball? So I'm going to turn both of our objects into spheres, and we'll call this object 1 and object 2. That's a good place to start. We need some numbers. I'm going to make our person object 2, and our ball, which is 15 kilograms, object 1. It has a velocity of 6 meters per second, and this has a velocity of 0. That's our kind of starting condition. Now, the way that we solve these is using conservation of momentum. And conservation of momentum says that the total amount of momentum in a system before things happen must be equal to the amount of momentum in the system after things happen. And the system is the combination of however many objects you have. In this case, we have 2 to begin with. So I'm going to write this as P1 initial plus P2 initial. Right? So 1 term per ball, I guess. Now, on the sort of final condition side, the person is catching the ball. So the way that I sometimes draw this is after the collision. So if this is the before and this is the after the collision, we are combining our 15 and our 90 kilogram objects. So this new thing has a total mass of the sum of these two objects, which is 105 kilograms. And because there's only one object, that means we're only going to have one term on the right-hand side, and that's P final. Once we have this, now we ask the question of what can I solve for? And I have enough information to solve for P1 initial and P2 initial. The formula for momentum is P equals mv. So P1 initial is 15 times 6. P2 initial is 90 times 0. So P1 initial is going to be 90 kilogram meter per second, and P2 initial is just going to be 0 kilogram meter per second. So now P1 initial is 90, P2 initial is 0. That equals P final. So that means our total amount of momentum is 90 kilogram meter per second. And all of that momentum now belongs to this new combined thing. So that means if we do one more P equals mv, do like P final is M final V final is how I sometimes write it. P final is 90, and our new object has a mass of 105 kilograms. So that's going to be multiplied by some V final. If we divide by 105, we get a final velocity of, I hope I'm right, great, 0.86 meters per second. And we should do a quick sanity check. Does this make sense? If we have a stationary person catching a moving object, and then the stationary person has a much higher mass, once they combine, they should be moving slower than the initial velocity of the ball, which was 6 meters per second. That is indeed a lower number. Thing number 2, it should have the correct sign. If the person originally was stationary and the ball had a positive velocity, that means the system has an overall positive momentum, meaning this new combined thing must also have a positive momentum, and because mass cannot be negative, it must have a positive velocity, which it does, so it passes those 2 sanity checks at least. Then we get to the elastic stuff, where the process is much the same, but we're going to have to look at just a slightly different scenario. So we'll do our sort of thing again, drawing our objects. We have 1 and 2. Let's do number 1 here. Whoops. Number 1. Ball 1 has a mass of 2.2 kilograms, and ball 2 has a mass of 3.8 kilograms. Initial velocity of ball 1 is 6 meters per second. Ball 2 is -8 meters per second. They collide and bounce apart after the collision, so I'm going to add some VI's here. After the collision, ball 1 has a velocity of -3. The question at hand is, what is the final velocity of ball 2? We're going to continue this with our conservation of momentum, sigma pi equals sigma pf. And doing the same thing that we were doing before, we're going to write a term for how many objects there are at the beginning and the end. So if this is our before, this is our after, the thing with an elastic collision is that the 2 objects remain separate, right? So initially we have 2 objects, and at the end we have 2 objects. So this is still 2.2 kilograms. This is 3.8 kilograms. And the thing that we do know is, we do know that VF of ball 1 is -3 meters per second. One thing we have to be careful about is we don't actually know what direction ball number 2 is going to be moving after the collision, and we can't know until we finish the problem. So you can't immediately draw an arrow of the direction of ball 2 if you're drawing a diagram like this. All right, so P1 initial plus P2 initial is going to equal P1 final plus P2 final. So because each object is maintaining its independence, we have 2 terms on either side. P1 initial is going to be 2.2 times 6, or a P1 initial of, this is 13.2, and P2 initial is 3.8, sorry for writing small, times -8. That's a P2 initial of 3.8 times -8, which is -30.4. So we've got here 13.2 plus -30.4, and that's going to equal P1 final plus P2 final. So 13.2. Add those together, we get -17.2, and that equals the sum of the 2 final momenta. So one thing to note here is that unless we know one of the 2 final velocities, this is not a finishable problem with only momentum. It is possible to solve these to find both final velocities if you use conservation of energy, but we haven't learned that yet, so we're not going to do that. What we can do is we can get P1 final, and that's going to be 2.2 times negative 3. And that gives us a P1 final of negative 6.6 kilogram meter per second. So we get negative 17.2 equals negative 6.6 plus P2 final. So now we kind of have to say, well, what do we do now? What conceptually is happening here? Essentially, the total momentum in the system is negative 17.2. If ball 1 ends up with negative 6.6 after the collision, P2 final has to kind of make up the rest of it. So negative 6.6 plus something must equal negative 17.2. We can solve for this kind of algebraically by adding 6.6. And if we get that, negative 17.2 plus 6.6, that gets us negative 10.6 equals P2 final. So if P2 final must be negative 10.6, P2 final is M2 times V2 final. So negative 10.6 equals, M2 is still 3.8 kilograms. So if we divide by 3.8, we get, and I sincerely hope I didn't mess something up in here, we get a V2 final of negative 2.79 meters per second. Do I agree with myself? Heck yeah. And what I mentioned earlier was we have to be careful not to assign, we might think, right, that two objects colliding and bouncing off of each other, that they would end up going in opposite directions. That doesn't end up being the case. In this scenario, both objects end up going negative. And I find that, that's interesting. That is absolutely a possible outcome of this kind of collision. So, in this case, like the is it positive, is it negative sanity check doesn't necessarily apply because the system is more complex. There's more going on, is my general point. Okay, let me see if that was it. I think it was. Okay, so with that, I'm going to call it. If you're coming across anything, while you're watching this or going over anything, please do email me. Technically, my workday is over, and we won't really have time to go over anything before the mid-year exam. But I'll do my best. If you can be the first person to walk into the room and get my attention, theoretically, I could attempt to help you, but no guarantees. And I think that's going to be that. So good luck studying, and hopefully that was helpful.